Okay, hey, we are in section 2.3, and I'm very sad that I haven't seen my two-way friends for the whole semester, but I know you're out there because you've been emailing me and you've been watching, I guess, the videos and trying to catch up, and you'll be fine. Today we're going to do the formal definition of a limit. So I dressed down. I guess I should have put a tuxedo on or something, but I got this cool, you know that store Amelia's? Have you seen that? You can buy, it's like a resale shop, and I got a really cool like designer dress. That would have been funny to wear that today. I wasn't thinking. But I wore my t-shirt because it's Friday, and the high schoolers that I did see, they all had their different schools on. Okay, anyway, we're going to do the formal definition of a limit. It's known to be a little challenging, but I will tell you that I think I've figured it out how to explain it, so I think you're going to be all right. But I remember the first time, or the first few times, it was maybe me not doing a very good job, and it is kind of a funky thing. But it really is kind of how you put your mind around it. So we will begin with a sort of an idea like an application to see why this would work or how we would be thinking this way. So suppose you're building a part of the space shuttle that requires engine cylinders with a cross-sectional area of 9 square inches. So you know what you want, right? You know you want a cross-sectional area to be 9 square inches. And then the question is, but you know, you have a machine that has to actually cut the cylinder, and it could have some error in it, right? And it could make some mistakes. And so what we need to say is, to 3 decimal places, what is the ideal diameter of a cylinder to obtain a cross-sectional area of 9 inches squared? So we know what we want. We need to figure out how much tolerance we can put in our or how we can calibrate our machine, how much tolerance we can allow in our machine, so that what we get is 9 square inches. Does that make sense? Okay, so let's do some thinking there. First, we want the ideal diameter, and then we'll talk about the tolerance first. But first we're going to look at the ideal diameter. Okay, so if you have a cylinder, it's like a Coke can, right? And maybe in geometry you remember that the cross-section of a Coke can, that means if you just took a knife and cut it, but don't do that at home because it gets really sharp. But anyway, if you cut a Coke can, it would make and then you looked at what you cut, you have a circle, right? Okay, so the cross-section is a circle. All right, and we want to force that cross-sectional area to be 9 inches squared, right? Okay, so if the diameter, say the diameter were x, so that would be the length here. Say this is x. If the diameter equals x, then does anybody remember the formula for area of a circle?
Pi r squared.
Good, everybody. So the area formula is pi r squared. And we don't want the diameter, we want the radius. So what is the radius in relation to the diameter? Right, the radius is the diameter divided by 2, right? Or here, half of x, right? Okay, and so we then know for our particular problem that our area is going to be equal to pi times x over 2 squared, right? And that's for our problem, or in general. And then for our problem, if we want the cross-sectional area to be exactly 9 inches, then we're going to put a 9 in here, and we will solve this equation for x, okay? So what we might want to do is go ahead and square this out. So we'll have 9 equals pi x squared over 4. And then multiply on either side by 4 over pi. So we get 36 over pi equals x squared. And then in order to solve for x, we would get x equals plus or minus the square root of 36 over pi, which is plus or minus 6 over pi. But here, x represents a diameter, so it doesn't make sense for it to be negative. The only reason I had the plus or minus is because when you invoke the square roots principle, like x squared equals 4, it could be 2 or negative 2, which makes that true. But depending on the situation, you may not need the negative. So in this case, we don't need the negative. Here, it's just 6 over pi. Okay, so the mathematician, 6 over, y'all were slow, square root of pi. Right? Oh yeah, that's what I was thinking. Yeah, whatever. Okay. Yeah. Okay, so, the square root of 36 is 6. We don't know the square root of pi. If we did, we'd be cool. The square root of pi is, gosh, pi is irrational, so how are you going to take the square root of it? Who knows? Now, if you, as the mathematician that works for the space shuttle company, says, no problem, calibrate your machine to 6 over the square root of pi, the engineer or the technician who's calibrating the machine would say, what? How am I going to do that? I cannot do that. Pi is not a number that I can put into my machine and cut it exactly to, right? Pi is a number that doesn't repeat or terminate, so it's impossible to actually ever hold on to it, right? Like you can hold on to 1 inch, right? So you of course would not even worry about it, and you would get a decimal approximation, right? Well, right there is where you start to incur error, because at the moment that you start to give it a decimal approximation, you're going to get a little bit of error. If you type 6 over the square root of pi into your calculator, you should get something like, if we did it to 3 decimal places, 3.385. Anybody else? Y'all agree with that? So if we do 6 divided by the square root of pi, we get 3.385 to 3 decimal places. Okay? And so if we use that as our radius, then when we computed our area, which is pi r squared, we would get no, this is actually our diameter because, remember, x was the diameter. So if we put that into the formula, we would do pi times r squared, which would be the 3.385 divided by 2, because that's your radius, squared. And if you hit enter, you get 8.999268871. So you're not at exactly 9 square inches, right? You're off by tenths, hundredths, thousandths, 1,000th, right? And maybe a little bit less than a thousandth, but you're still off. Okay? Does that make sense? All right, and so the real world, you're always off a little bit, and you have to give some sort of tolerance. And you have to kind of talk to the engineers and talk to the technicians in a way of, all right, this is what I want. Please calibrate the machine so it gets within this interval of what I want. And because of the algebra or the calculations that you're going to be doing, you actually have to be more precise in your cutting to get a certain precision in the end. Do you know what I'm saying? Because your cut will have error. The error will compound as you do some formula to it. Like when you square it and it's got error, that's going to increase the error. So you can't just say, if you want it to be within 1/10 of an inch, you can't just go down and say, okay, then I'll just cut it within 1/10 of an inch on either side. It's not going to work. Does that make sense? Okay. Always makes me think of when they're building those. You ever seen how they build those highway crossover? Every time I look at one of those, I always wonder, is it going to meet? Because, they start at one side and they've got this big thing coming, and then they start the other side, and then they're in the middle, and they always meet. There's a lot of math going on there because they're bending. It's crazy what's going on for that. Something so simple, but for that to happen, it's such a dance between the applied math and the real math, and then the engineers and the guy pouring the concrete and everything. Okay, so the machines that are used to grind the engine cylinders are not perfect. Suppose you can tolerate a deviation of 0.01 square inches in the cross-sectional area of the cylinder. Write an inequality that would illustrate this tolerance. So what do you think that means? What is it that you can tolerate? Well, you can, what is as much as you would stand? You wanted it to be 9 square inches, but you will tolerate 9.01 or 8.99. Does that make sense? You'll go on either side of that. So you're like, okay, machine guy, 8.99 to Robinson, yay, 9.01. Here, we'll stop for a second to say hello. Hey.
Hello, Miss Brooks.
It's been a good week.
No. I think this happened only because you guys called us.
Oh, the only reason that you're here right now?
Yes.
Oh.
It's still not perfect.
I'm sorry. Okay, well, I'm sure it will be perfect soon. The website's perfect. Have you noticed how awesome it is, how you can still learn even when you don't have a teacher?
Yes, we're very pleased with that. We were getting ready to go to the website because
I
we're not
actually
going to
think
waste
that's a
time.
good idea in the future. Do know that I have the old videos up there, and at the very bottom I have the live videos for that we're doing right now. And so at the beginning of class, I'll try to wait till y'all get in. At the beginning of class, what we've been doing is just answering questions, and I've been making little videos that are under the homework help button. So if you're working on a homework question and you have a problem, you might check under lessons and then homework help. I've made quite a few videos under there. Okay? So I'm going to we're looking at section 2.3. I'm going to pick up with that. Is that okay? Are you too sad?
Yes,
Robinson?
that's fine.
Because we're probably going to leave.
That's fine.
All right.
Well, we're also, Mondays and Wednesdays we'll catch the beginning, and Fridays we'll be catching the end because of our pep rally schedule.
Okay.
But either way, we catch the whole thing online.
That is right. And you're sophomores in college in this class, so remember that when you're crying at home. You're not going to cry at home, though, because you've got to be pretty geeky to be in this class as seniors, right? Are they? Oh, what was that for? Was that because you've already cried at home, or because you're a geek?
That's because it's a sophomore level class, and they think they're awesome.
They are awesome. Sophomore level, 4-hour credit. You're doing really good. But I realize that it's tough, and so I'm sorry. Okay, I'm going to finish. I'm going to keep working on this lesson, so I'll see you as I see you. Are y'all okay? We saw you online.
Yes, we're fine.
Okay.
Thanks.
All right. So this lesson will have a little introduction in the middle of it. Do you want? Here's our family. Y'all wave. There they are. We have lots. How many girls do we have at Robinson?
We have 4 girls and 4 guys.
Oh, yay. We have one girl. We have Courtney here. She's all by herself. And me. I promised that there were more girls at Robinson. Okay. Back to the laptop. All right. So we're saying that our machine that we have, I will tolerate 1/100th of an inch. And so this machine creates cylinders for the engine. Okay. So I will tolerate to 8.99 to 9.0 square inches in my area, and that's what I'm talking to the person who's building the cylinder for. So he has to figure out, or she has to figure out what diameter, or what diameter, and then also what tolerance they should calibrate their machine to. And it won't be 0.01. It'll actually be even more precise, because what happens when you go to compute the area, you incur more error, and so you have to be more precise. Okay, another way to state this is with absolute value symbols, okay, because absolute value just means on either side of, and you might think of 0, like the absolute value of x is less than 5, means that you're between -5 and +5. You're sandwiched in between, right? Because absolute value is really just kind of your distance from 0. Well, if we said, well, my distance or my area tolerance between what I actually want, which is 9, has to be less than or equal to 0.01. Does that notation make sense? I'm sandwiching the difference between the actual area and the desired area has to be between 0.01. Okay? So this error right here, this error, we're going to call our epsilon tolerance. This is epsilon. It's a little sort of a C with a line in the middle. You get to learn Greek letters today too. It's all, you got it all going on. Okay, so now let's play with what we know. We knew a minute ago, we were in, let me just for Robinson's sake, here's our cylinder. The cross section, if you cut it, is a circle, and the area is pi x over 2 quantity squared. The area is pi x squared over 4 is what the cross-sectional area would be in general. So if I were to replace A with pi x squared over 4, I could then get a formula in terms of the diameter, or an equation, or I could figure out a calculation for the diameter. Okay, so just solving this for x squared, the first thing I'll do is multiply both sides by 4 over pi. Okay, and then I would take the square root of both sides. So, and then again, the plus or minus is not necessary because we're dealing with a real thing, so it can't be negative. Okay, and then remember, if you type this in your calculator, it's going to do its own set of parentheses there. But when you type it into your calculator, you should get 3.383 is less than or equal to x, which is less than or equal to 3.387. So I'll just show you, if I type that in here, if I do second square root, I actually, because this is a product, a product and division, I can just do 4 times 8.99 and divided by pi. I could actually do 4 divided by pi times 8.99 without any parentheses, and the calculator would know what to do, but it feels uncomfortable to students, I think. But anyway, there's my 3.383, and then the same on the other side. Okay? So that's my approximation. Now, what was the ideal? This 3.385 was if I was using 9. Now, it wasn't ideal because we couldn't. The ideal was 6 over the square root of pi, right? But let's just say to 3 decimal places, 6 over the square root of pi was that 3.385. So 3.385 was the ideal, and 3.387 is on this side, and 3.383 is on that side of the ideal. Are y'all with me? Now, this distance on either side, in this case, is the same. 3.387 minus 3.385 is 0.02, and 3.385 minus 3.383 is also 0.02. That's not always true, but in this case, it is. And oh, did I miss a 0? Is that what you're telling me? Is that why you gave me that? You could be louder. Okay, 0.002, 0.002. All right, and so this then is that 0.02 is called my delta tolerance. So 0.002. That's the tolerance that I can allow. I can only be within, in order to be within 0.01, 1/100th on my area, my diameter has to be within 2/1000ths. So you have to be more precise in the diameter that you cut in order to get less precision in the area. Does that make sense? Sort of? Okay, so if it had, through rounding, turned out that this distance from the ideal to either one of the endpoints was not the same, to be conservative, what would you do? Remember, you're instructing them on what you want what the tolerance of the diameter cutter has to be. If, say, this one was 0.003 and this one was 0.002, what would you tell them to use? Which of those numbers would you tell them to use? Yes, go with the more conservative, right? Because then you're guaranteed. So you always choose the smaller delta. It could happen that your delta tolerances are different on either side, and you always want to choose the smaller delta. Okay? All right, so number 3 is what I just did. I done did that. Okay, so I did that. I found it to be the interval is 3.383 to 3.387. That's the interval, and the tolerance is 0.002, and we call that tolerance the delta. Okay, now it says, what if we could only tolerate a deviation in the cross-sectional area of 0.001? Could we find an interval of allowable diameters? Could we do that? Sure. We just have to, it would be a smaller interval, but we could do that. And what about a tolerance of 0.0001? Yes, we could do it. So for any requirement that I give you, as close as I want to be to the area, you would be able to give me a diameter tolerance. Now, whether you would be able to physically do it with the machine that you have, that's where we're going into the weird world of imaginary math, right? But in the sense of, I give you a restriction on the area, you give me a restriction on the diameter, we could always get there. We could always do it. So I could do it mathematically using the same process. As step 2. And like for the first one, I would just say that I need to be in between 8.999 to 9.001. And then I would just continue. Okay? So that's the concept. That's the idea that we're looking at when we are thinking about the formal definition of a limit. If we think of the cross-sectional area as a function of the diameter, then for any requirement we place on how close the area needs to be to 9 inches, we call this the epsilon tolerance, we are able to find an interval containing the ideal diameter, which we would call that x naught, that's your ideal x, that will produce cylinders within the epsilon tolerance. The smaller distance from x naught to either endpoint of the interval is called the delta tolerance. Okay? So given an epsilon, I will be able to find a delta to make it work. This is, now we're talking like Cauchy and Chebyshev and all those really fancy mathematicians after Newton and Leibniz. Okay, now we're getting very precise in our description of the limit. Okay? We can still do limits all day long because we can just plop them in our calculator. But if you want to be a cool mathematician, you have to throw some epsilons and deltas and some notation in there that scares people, which is what we're going to do now. The formal definition of a limit, you should memorize it. Unfortunately, the tests are online, and it's really hard for me to test whether you have this memorized. But if you don't have it memorized, you will live a very sad life. Okay? And you never know when I'm going to see you at Tuesday night and it's that taco night and at, what's that place? Rosa's. And you're like, Miss Brooks, and I'm like, what's the formal definition of a limit? And you're like, okay. And then I'll give you a big F for the semester. All right, let f of x be defined on an open interval. What am I going to say next? If you've been memorizing my lectures word for word, you would know that I was going to say, except possibly, remember that part? Okay. So with open interval about, some point, which we're going to call x naught, except possibly, this at x naught itself. That just means you can have an open circle at the point itself, but on either side you have to be coming into the same value, right? We say that the limit of f of x as x approaches, I don't like that word because it says the word roach in it. I don't like roaches. Approaches x naught is the number L. And right, okay, here's the part you really memorize because it makes you look very, very cool. The limit as x approaches x naught of the function f of x equals L. This is true if, okay, I'm going to get fancy on you. You ready? In math, if you want, you say for every all the time. So there's a shorthand code for every, and it is a V with a line through it. This means for every. For every epsilon, remember that's the C sort of thing. Actually, it's more of a, yeah, it's fine. It can be more cursive-y too. I think it should be more cursive-y. So it's going to be like a cursive-y. For every epsilon greater than 0, okay, in math you also say there exists a lot. So you use a backward E to keep yourself from having to write there exists and to look cool. So if for every epsilon greater than 0 there exists a number delta greater than 0, and then in formal math you often use the word such that, and so we have a little code for such that, and that's the little backwards C with a line through it. This is the code for such that. For all, or for every x, whenever 0 is less than x minus x naught, which is less than delta, that implies that the absolute value of f of x minus L is less than epsilon. Okay. So you will always be able to find a delta tolerance that will give you your desired epsilon tolerance. That's what that's saying. So if you're really cool, you can write if for every epsilon greater than 0, there exists a number delta greater than 0, such that for all x, if you know that x is within some certain tolerance, you will be able to get your function to be within epsilon of the limit. Okay? So that's it. That's the scariest thing you'll do in the whole semester. The rest of it's algebra, and if you were bad at that, it's not my fault. Okay? This is it. And it's not really that scary. It actually looks pretty cool. I mean, like, you go home and show that to your parents, and they'll be like, oh, yeah, there's $500 well spent. Or maybe it wasn't even 500. Okay, so here we're going to actually do some math problems, practicing using this formula. It's actually kind of fun. And I bet you're going to get really good at it. So, and this is what the online homework is. For problems 7 through 10, the given function f of x and the values of L, x naught, and epsilon are given. Given function f of x and values L, x naught, and epsilon greater than 0. Find the largest open interval about x naught on which the inequality holds, then determine the largest value for delta such that, you know, the theorem will in fact be true. I mean, look at just that. Just show them that. They'll be like, oh, yeah. Okay, so a lot of times when you're working with math, you start with what you want and try to get to where you or what you hope to know, and then you try to get to where you want to be. Okay, so the idea here is that if this limit definition is true, we can put all the different things that were given into this function, right? the limit as x approaches x naught of f of x equals L. So the limit as x approaches x naught of f of x equals L here will be the limit as x approaches what? Perfect. 5 of f of x, which is 3x plus 8 equals 23, right? Just popping in the different stuff. Of course, this limit you could just compute by hand because 3 times 5 is 15 plus 8 is 23, just a little plug-in. So we're doing, it's kind of silly what we're doing. But anyway, we have this epsilon tolerance that we want to deal with. So we are going to say, we're going to take the last part of the proof. The absolute value of f of x minus L is less than epsilon. So we're going to begin with that, and we're going to work backwards. The absolute value of f of x minus L is less than epsilon. So in our problem, that is the absolute value of f of x, which is 3x plus 8, minus L, which is 23, needs to be less than what? Very nice, 0.3. Okay, now it's a math problem. Because what we're going to do is we're going to get, if we solve this math problem, we will get an x interval, right? And we know what our ideal x is. What's our ideal x? I heard it, Courtney. Perfect. This is the ideal x. X naught is your ideal x. So when we have our interval, our ideal's in the middle, and we can just find the distance from our ideal to the on either side. Y'all with me? Okay, so this is, we can clean this up. We can clean it up. We can say, and we can do I'm going to do 2 steps. When you have the absolute value and with a less than, I like to get rid of the absolute value bars and make a sandwich, all right? So that thing less than 0.3 means it's sandwiched between negative 0.3 and positive 0.3. It's on either side. The distance is 0.3 on either side. So this is negative 0.3 is less than this thing, 3x plus 8 minus 23, which is less than 0.3. Okay, and this one's not so hard to clean up. Negative 0.3 is less than 3x. 23 minus 8 is minus 15, which is less than 0.3. Now, you have some options here. I'm just going to solve for x. This is different than I did the lecture last time. Okay, I'm going to add 15 to both sides. And so this will be, so plus 15, plus 15, plus 15. So that's what, 14.7 is less than 3x, which is less than 15.3. And then I'm going to divide everything by 3. And I get my interval to be, anyone? 4.9 to 5.1. 4.9 is less than x, which is less than 5.1. Okay? So that is the interval. As long as my x is within, as long as I select x's within 4.9 and 5.1, I will get L's that are within 0.3 of the true value of 23. So 23.3 to 22.7. Does that make sense? So as long as I limit my x within there, I'll be able to get a y within that certain tolerance. Okay, and so what is the delta then? This is the interval, 4.9 to 5.1. Well, remember the ideal was the x naught value, which here was 5. So the delta is just the smaller of the distance from the ideal to either endpoint. Okay, now in this case, it's 0.1 on either side, right? So our delta is equal to 0.1. So notice we have to be more precise in our delta than our epsilon. Our epsilon tolerance was 0.3. In order to get a 0.3 epsilon tolerance, we had to be 0.1 tolerant in our delta. And that has to do with the fact that you're doing something to the x, right? You're multiplying it by 3 and adding 8. Not so bad? This is really the homework part of it. This is all we're doing. It can be more algebraically challenging, but otherwise it's not. It's kind of fun. Okay, so what I like to do if I have a problem here, I'm going to look at the limit now. Does I don't know, Robinson, are y'all there? Can you unmic? Do you have the mic right there? Could you push a button or no? And you could tell me how I'm going to set up this limit given the problem. Did she give it to you or no? Or did you have to leave all this stuff? All right. I think you just push a button.
We have it.
Okay. So look at this problem and set it up in limit form for me.
Go, Mike.
I know. All you have to do is fill in the
We're having
parts.
difficulties.
You can do it. Oh, they're too nervous. It's hard to be on camera. And they're like dressed up for something today, I think. Is it hippie day or something?
It's injure the Indians today.
Oh, Indians, okay. Yeah. All I need is for you to put the different parts in. I'll get you started. So this is the limit as x approaches 5 of, what's the f of x? This is easy. You'll feel good. You can even miss it. Nobody would care. Turn off the mic and tell me what f of x is. They're scared.
The square root of 6x plus 9.
Perfect.
91.
All right. Is equal to
11.
There we go. Okay, so that's easy, right? All right, so that's what that means.
Yes.
And that means, of course, this is a plug it in. You put 5 in here, right? 5 times 6 is 30, plus 91 is 121. The square root of 121 is 11. So this is no big deal, okay? So now we want to figure out what our delta tolerance needs to be in order for our epsilon to be within 0.08 of 11, okay? So we start with the end. The last statement of the proof, the absolute value of f of x minus L has to be less than epsilon. So we're going to look at that. The absolute value of f of x minus L, we want that to be less than epsilon. So for this problem, we want the absolute value of the square root of 6x plus 91 minus 11 to be less than 0.08. Everybody okay? All right. And so then that means that, what does this mean? Sandwich it in between negative 0.08. So negative 0.08 is less than the square root of 6x plus 91 minus 11, which is less than 0.08. Okay? Then we will add 11 to either side. And so we will get, if you do 11 plus negative 0.08, it's going to be 10.92. Is less than the square root of 6x plus 91, which is less than 11.08. How do I get rid of the square root? If I square everything, I'll get rid of the square root. So I will do 10.92 squared is less than, if I square that, I just get 6x plus 91, which is less than 11.08 squared. Are you okay?
Yeah, I'm trying to just get you.
I'm speedy. Okay. Now, in the interest of precision, I am not going to figure out what 10.92 squared is because then I would have to round it. Okay. And since I have my calculator, I'm going to type it all in one line so I don't have any rounding error. So I will just subtract the 91 and divide by 6. So this is 10.92 squared minus 91 divided by 6 is less than x, which is less than 11.08 squared minus 91 divided by 6. Everybody with me? Okay, and then at this point, you can type it into your calculator. Do be careful when you type something like this into your calculator. You're going to want to use parentheses in the numerator. So you can do parenthesis 10.92. And you can actually, you don't need the parenthesis, you can just pop a squared right there, and then minus 91. Here's where you have to close the parenthesis to get your whole numerator in, and then divide it by 6. So we get 4.707. This is kind of cool. Have y'all seen this? If you do second and then enter, you can pull up whatever you've previously typed in your calculator, and then edit it, because all we need is to change this to 11.08. So we get 5.2944. 5.2944. Okay, so that's our interval. I'm going to do it to 4 decimal places. They'll tell you on the online homework what kind of decimal rounding they want. So this is 4.7077 is less than x is less than 5.2944. And so then the interval, on the homework they actually asked for the interval, is going to be 4.7077 is less, comma, 5.2944. And then to find delta, what do you do? Right, you put, what goes in the center? 5. The ideal value, which was, in this case, 5. So that's unfortunate. Was it 5 in the last one? No. But you got that changes, right? It's your x naught. Okay, and so we do 5.2944 on that side and 4.7077. And if you find the distance from this to this, obviously that one's 0.2944. This distance from the ideal to 4.7077 is 0.2923. You always choose the smaller distance for delta. That guarantees what you want to happen. So you always choose the smaller delta. Choose smaller distance. Distance for delta. So here, delta is going to be equal to 0.2923, because that's just a little bit smaller than 0.2944. Not so bad? No, Mrs. Brooks, this is awesome. Good, let's do 2 more. Okay. All right, so number 10, I'm not going to do that. Do you want me to write the limit thing again, or y'all with me? Can I jump right into the, okay. So I will jump into the end of the proof, f of x minus L, absolute value has to be less than epsilon. With me? All right, and so in this case, the absolute value of the square root of 30 minus x minus 2 has to be less than 0.1. Okay? Then we make the sandwich. So this is negative 0.1 is less than the square root of 30 minus x minus 2 is less than 0.1. Then we add 2 to both sides in order to clean this up a little bit before we square both sides. So this will be 1.9 is less than the square root of 30 minus x, which is less than 2.1. Now we square both sides, and we'll get 1.9 squared is less than 30 minus x, which is less than 2.1 squared. Now these numbers, 1.9 and 2.1, both square easily, so I will go ahead and say what they are. On your calculator, you should get 3.61 is 1.9 squared, is less than 30 minus x, which is less than 2.1 squared, which is 4.41. Okay, now I did choose this one because it is a little bit, it's a little bit tricky when you're solving for x. If I subtract 30 on either side, 3.61 minus 30 is negative 26.39 is less than negative x, which is less than 4.41. That's negative 25.59. Everybody with me? Now, yeah, did I see you already? Yeah. When you divide by a negative, it flips the symbol when you're working with inequalities. Do y'all remember that? So when I divide this by negative 1 on either side, it is going to flip the symbol. So this symbol and this symbol are both going to flip. It makes sense that it would anyway, because otherwise it would be weird the way that it would work. Okay, and so you get, well, if it flips, can you feel the whole rotation then? I mean, you sort of feel the whole, whole thing. All right, so this is going to be 25.59 is less than x, which is less than 26.39. right? And so my interval is exactly that, 25.59 to 26.39. And my, if I put that on a number line, what goes in the middle? It was the original value, yeah, the x naught, which is 26. So here's 26.39, and here's 25.59. And then this length, if you just find that length on your calculator, 26 minus 25.59 is 0.41, and this length is 0.39. So what is your delta going to be? Because this is my x naught. So delta, always pick the smaller. And so here, delta is going to equal 0.39. Okay, so I did that one because of the flipping. Remember the flipping when you divide by a negative. Okay, and then number 10 is exciting as well because you may not have done an inequality with a rational function. It may have been a while. It's kind of a fun one too. Okay, so on number 10 we have, how do we start these? I forgot.
Value f of x minus
Less than epsilon, right? Y'all with me? We get the delta. We have the epsilon, we get the delta. Okay. So this is the absolute value of 1 over x minus 0.05 is less than 0.02. And then we make the sandwich, so this is negative 0.02 is less than 1 over x minus 0.05, which is less than 0.02. Yeah, we'll add 0.05 to either side, so we'll get 0.03 is less than 1 over x, which is less than 0.07. Okay, now, this may not be totally obvious to you, but when you reciprocate a compound inequality like this, it will actually flip the symbols as well. For example, say if you just thought of, say you thought 2 is less than 1 over x is less than 8, right? Now, if you were to flip it all, right, you would have 1/2 x and 1/8, right? But if x is in between, this is going to have to go like that. Do y'all see it? You see what I'm saying? Okay, so that is the same is true here. If I flip this, it's going to be 1 over 0.07 is less than x, which is less than 1 over 0.03. Does that feel okay? I don't know if you've ever seen that, but it's very exciting. Okay, and so then 1 over 0.07, if you calculate that on your calculator, is 14.2857. Is less than x, which is less than 1 over 0.03, which is 33.3333 forever. All right, and so that is my interval, 14.2857 to 33.3333. And that makes, I draw the line, I pop the, what was my x naught? 20 here. That's interesting. It's going to be a big delta, isn't it? So 33.3333 and 14.2857. And they'll tell you on the computer how much to round to. So I guess I was just doing this based on what they said. Okay. So this distance is 13.3333, but this distance is 5.7143. And so my delta tolerance will be what?
0.713.
There we go, 0.7143. You, everybody, I didn't do those competitions. You always pick the smaller delta. Okay? So, like, there's worse sections, right? It wasn't too bad. The actual work of it's not too bad. So the idea, now, how does this become formal? Because it was actually the moment we started putting numbers in it, we got informal again, right? It was formal when it was weird with these letters, right? And what we're trying to say there is that you can ad nauseum, you know, you can find, I can give you, it's like a dance between the, how have I heard it described, between the doubter and the person that's trying to prove something. It'd be like, well, can you pick one in .01? And you'll be like, well, yes, if you use .002. Well, what about .001? And he says .004. And and it's like a back and forth, right? You're always able to get an X, close enough in the X to get as close as you want to the L, to the limit. So that's what, if you're always able to make that true, for any tolerance I give you for epsilon, for the limit, I can always give you a delta tolerance. If that's true, then you know that the limit exists. Does that make sense? So it's kind of like deep when you only have letters. But when you actually do the problems, it's not so bad. Yeah, for any, I could change those. You know, at any of those, I could change what I wanted my epsilon tolerance to be, right, at any moment, and you would always be able to get me the delta tolerance. Okay, all right, Robinson, we finished early. Do y'all just want to hang out and talk?
Our bell's just tasting the ring. But thank
Oh, it
you.
is. Okay.